Bismillahirrahmanirrahim. This is teacher Iman explaining Chapter 7 Integrations. Theorems of Definite Integrals done by teacher Iman al-Khalidi. Theorems of Definite Integrals Integrations. We have many theorems on that lesson. So we are going to mention them now all and then discuss each individually. Number one, if f of x is continuous on the closed interval from a to b, then f is integral on the interval a to b. Two, if c is a constant, then the integration from a to b for that constant c d of x will give you c times b minus a. 3. If f of a exists, then the integration from a to itself a f of x dx will give you 0. Number 4. If f of x is integral on the closed interval a and b, then the integration from b to a of f of x dx equals minus the integration from a to b f of x dx. If f and g are integral functions on a and b, and k is constant, then f plus and minus g and k times f are integral on the closed interval a and b. Then we can have the following theorems. Number 5, the integration from a to b for the constant k with the function f of x dlx will let k goes outside from a to b of f of x dx. 6, the integration from a to b of f of x plus and minus g over x for dx equals the integration from a to b of f of x dx plus and minus the integration from a till b of the function g over x dx. Number 7, if f of x is integral on the closed interval a and b, and c is between a and b, then f of x is integral on the closed interval a and c, and the closed interval c and b, then we can write the integration from a to b f of x dlx equals to the integration from a till c f of x dx plus the integration from c to b of f of x dx. Number 8, if f of x is integral on a and b, and f, the function f of x, is bigger than or equal to 0 for all x on the closed interval a and b, then the integration of a and b f of x dlx bigger than or equal to 0. Number 9, if f of x and g of x are integral on the closed interval a and b, and f of x is bigger than or greater than or equal g of x for all x belongs to that closed interval a and b, then the integration from a till b f of x dx will be bigger than or equal to the integration from a till b gx dx. The last is if k and l are two real numbers, and f of x between k and l for all x belongs to the closed interval from a to b, and f is integral on a and b, then the integration from a to b of f of x dx will be between k bracket b minus a and l bracket b minus a. Now let's discuss these individually by taking some examples for each. Before of that, we need to know what do we mean by integral. Definition: if the limit when n approaches to infinity of b minus a over n with the summation I equals 1 till n of the function xi star exists. This all we took it before when we discussed the definition of the definite integral. Then the function f of x is said to be integral on the interval a and b. So to understand what do I mean by the function integral, the function is integral on the interval. That means the limit of that definition exists. The limit of delta x multiplied by the summation exists. And the limit exists when we can have an area bounded between the curve and x-axis and the two vertical lines. And these were discussed before in the previous lesson. Now let's start by the first definition, the theorem, the first theorem. Theorem number one. In theorem number one, you can see that if f of x is continuous on a and b, then f is integral on a and b. Integral means we can calculate the limit and find it exists. Continuous, we can see it in the graph later. We can write it in that way. Integration from a and b of f(x) dx exists. The converse of this theorem is not true. When we're going to say if f is integral on a and b, then f of x is continuous on a and b. This statement is false. In case if the function is discontinuous, we can calculate the area under the curve, but the function is discontinuous. For example, in the following graph, look, we have that region and we have that region, and they are discontinuous. When we are going to calculate the area in this region between the curve and the x-axis and between that curve and the x-axis, you can calculate the area, but you can see that the function is discontinuous. So this statement is false. Now let's go to theorem or some applications about theorem number one, because it is really important. From ministry questions, a true or false. Number one, if we're going to say that integration from negative 3 till 0 for the function 1 over x dx exists. This statement actually is false because of the function 1 over x, as you know, is not defined at 0 on the closed interval from negative 3 till 0. Number two, the integration from negative 3 till 0 for the function square root of x dx exists. This statement also is false because of the function root of x cannot accept negative, is not defined on negative 3 and 0. Number three, from negative 3 till 0, the integration of ln of x dx exists. This statement is also false because of the function of ln of x, by going back to the graph of ln, is not defined on negative also. Like the square root, ln and the square root do not accept negative. So it can't be defined from negative 3 till 0. And they are not continuous. So because of that, the limit is not exist. And that means we can't calculate the limit, we can't calculate area. If f of x equals 9 minus x squared, then it is integral on the interval from negative 3 till 3. This statement is true because it's a polynomial, and polynomial is defined for all values, all real values, and it can be continuous also. So it is integral for any subinterval from R because the function is polynomial and it is continuous on the following interval from negative 3 till 3 or any interval. The next, we are now going to discuss other theorems individually. Let's now go to theorem number 2. If C is constant, then the integration from a to b for that constant value in terms of Lx will be equal to, keep that constant outside as it is and multiply it by b minus a. b minus a. Let's have examples to understand this theorem more. Example number 1. If we have an integration from 1 to 3 of the constant value 5 dx, you are going to keep 5 outside as it is constant, multiplied by 3 minus 1. Apply the theorem. And that means you will have 5 times 2, which is 10. Second, integration from -1 till 2 of 1 over 3 dx. 1 over 3 is constant because there is no variable. Keep the constant out and subtract b minus a to get 2 minus minus 1, which is 3. 1 over 3 multiplied by 3. After canceling a 3 with 3, you will get 1. Example number 3. Integration from 0 to 1 of the root of 3. This root also constant. There is no variable beside. In terms of x equals to square root of 3 multiplied by 1 minus 0. And that will keep it root over 3 multiplied by 1, which is root over 3. Number 4, integration from 0 to pi over 2, sine pi over 2. There is no variable. There is no x. That means sine pi over 2 can be calculated. And that will keep sine over pi over 2 as a constant value outside, multiplied by b minus a, which is pi over 2 minus 0. And that will be after calculating sine pi over 2 is 1 times pi over 2. And that will give you finally pi over 2. Example 5. From 0 to 2, the integration of len 2. Len 2 is irrational number and there is no variable, so it is constant. In terms of x, you will keep that constant as it is, multiplied by 2 minus 0. And that will keep 2 from here, multiplied by len 2 as a result. Number 6, integration from 1 to 2 for e2 dx. There is no variable with this function, so it's constant. So keep it as it is and subtract b minus a by subtracting 2 minus 1 and keep e2 outside, multiply by 1, and that will keep it e2. Number 7, integration from 0 to 3 sec 0 dx equals to sec 0 is a constant. There is no variable inside. So multiply it by b minus a, which is 3 minus 0. And you can see that 1 over cosine is 0 is how to calculate sec, which is multiply o by 3. And cosine 0 is 1. 1 over 1 is 1. Multiply by 3, which is a 3. I think we get theorem 1, theorem 2 by 7 examples. Let's now go to theorem number 3 to understand. If f of x exists, then the integration from a point to itself of f of x dx equals 0. That makes sense when you are calculating in area from a point to itself. Any area from a point to itself has no region. So because of that, its area is 0. Let's have examples. Number 1, integration from 4 to 4 for any function dx will be 0. Whatever the function is. Integration from 3 to 3, whatever the function is complicated, don't look at it, just make it 0. Don't think about it, just make it 0 because it is from A to A, from 3 to 3, no region between. In number 3, integration from 2 to 2 for e to the power of negative 2x dx. Even so, because it is from the point to itself, it is 0. Number 4, integration from 2 to 2 for len x dx, whatever the function is 0. Now, theorem number 4. If f of x is integral, what do we mean by integral? That means the limit is exist and we can calculate area. On the interval from a to b, then the integration, if it is written from the biggest to the smallest f of x dx, this is not allowed. You're supposed to change it from the smallest to the biggest by taking a negative as a common factor. That means you are making a switch between them, so you are taking a negative outside as a common factor. Let's have some examples. If we have an integration from 4 to 2, look, 4 is bigger than 2, and this is not allowed to integrate. So try to switch between them and take a negative outside as a common factor. Example number 2, integration from -1 to -3 of half dx equals to. Also, you have to make a switch and take a negative as a common factor, and that will keep it as it is, but make it from -3 till -1, and the negative is outside as a common factor. Now, because you have half is a constant, we can go back to theorem number 2 and use it again. That means you can keep half outside as a common factor and try to multiply b minus a, which is -1 minus -3. And that will make it later on 2, which is going to be cancelled as 2 divided by 2 to give you 1. Example 3. The integration from pi over 2 to 0. You can see that from bigger to smaller, it is not allowed for sine pi over 6 dx. That means you are going to take a negative as a common factor and switch the limits of the integration from the smallest to the biggest and keep the function as it is, sine pi over 6 dx. Let's go back to the theorem number 2 and apply it again like we did in example 4. Take it outside as it is and multiply it by b minus a. Pi over 2 minus 0 equals 2. Half multiplied by pi over 2 minus 0, which is after you multiply numerators together and denominators together, you will get pi over 4. Now we can go to theorem number 5 and understand it. If f and g are integral functions, what do we mean by integral functions? That means we can have or we can calculate the limit when the summation of delta x multiplied by f of x is exist, and or we can calculate the area under the curve on the closed interval from a and b, and k is constant. Then f plus and minus g and k times f are integral also on the interval from a and b. So what do we mean by that? If the functions are integral and the k is constant, their sum or their difference also are integral. So we can calculate the limit for them or the area under the curve. And then number 5, which is theorem number 5, is saying the integration from a to b for a constant value multiplied by a function dx will allow this k to go outside as a common factor. Then we can integrate the function itself. In 6, we say that the integration from a to b for the sum of two functions or the difference of two functions will allow this integration to get in to each. That means I can integrate the first alone plus or minus and integrate the second alone. But we can't do that with multiplication or division. We can't do that. Let's have some examples. Examples, we have an integration from 3 to 5 of 4 f of x plus or minus 6 g over x dx. You can let this integration get n for each, for the plus and minus, and integrate this alone and integrate this alone. And the constant can be taken as a common factor in each. Exactly like that. Equals 4 is a common factor. The integration over 3 and 5 of x dlx. Then a plus is 6 going to be taken as a common factor. Then you can integrate from a 3 to 5 the second function g over x dlx. Let's now go to another theorem, which is number 7. If of x is integral on the interval a and b and c is between and a and b. We say that many times. If is integral means the limit exists and we can calculate area. So if C between A and B, that means there is a point appears between A and B. So how to calculate the integration or the area between them? Then f of x will be integral on the interval, the subinterval from A and C, and subinterval from C to B. Then we can calculate the integration from a to b for f of x dx equals to by integrating the subinterval from a to c f of x dx plus the integration from c to b f of x dx. This means I can separate my area to two regions, to be from a to c, then from c to b, then add them together. Examples. For example, if I'm going to find an integration from negative 2 to 2 f of x, and there is 0 between them. For example, I can integrate it from negative 2 to 0 and a plus from 0 to 2 to get the same value. Now let's discuss the next theorem, which is 8. If f of x is integral on a and b, that means I can calculate the limit, and the limit exists, and I can calculate the area under the curve. And if of x is positive, that means the function is above the x-axis, has all positive values. For all x on the interval from a and b, then the integration, which is the area under the curve, also will be positive. The integration will be positive when the function is positive. Do you think this theorem can be oppositely same if we're going to talk about it when it is negative? Yes, it is. That means if the function is negative, so its integration will be negative. So we can have this function in two ways. If the function is positive, its integration is positive. If the function is negative, its integration will be negative. Of course, it will be negative if it is below the x-axis. Now, let's have some examples. Example, the integration from 1 to 3 of the function x squared negative 1 dx is bigger than or equal to 0. You can prove it by many ways. For example, you can prove it by sketching the graph and see that this graph is above the x-axis. So its integration is positive. But we can explain it for you by many ways. Now, let me give you some ways. The first way, by choosing a number between 1 and 3 and replace it in the function, like x equals 2. And if you're going to replace it instead of x here, that will make it 2 squared minus L1. And that will be 4 minus L1, which give you a positive number. So that means the whole thing is positive. So if the function is positive, its integration is positive. Done. The second way, by building the function method. That means I'm going to build the function. How? Let us see. To build the function, you're going to start by the value of x. You can see that x is defined from 1 to 3. So this is your interval. Is defined from A to B, from 1 to 3. And it can be written in that way. X is between 1 and 3. Then you need to build your function by looking to what is going on to x. X is squared, then subtracted by 1, then integrated. So let's square it first. First, you can square both sides. Watch it. If you square it, you will get 1 here, x squared, and 9. Then you will subtract it by 1 for each side. And subtracting or adding will do not change the symbol of this inequality. Watch it. You can get 1 minus 1 smaller than or equal to x squared minus L1 smaller than or equals to 9 minus 1. You will get finally 0 smaller than or equals to x squared minus 1 smaller than or equals to 8. Then you can see that x squared minus 1 is smaller than or equal to 0. That means this part is what we are looking to. Because of that, I ignore that part because I need to know if my function is positive or negative. So I can see that my function now is positive. which make which makes that interval from 1 to 3 of x squared negative 1 dlx is positive, because I proved that the function is positive. So the interval or the integration of that interval will be positive. This is the first way and the second way, and I give you the third way by graphing. The third way also by factorize it, then study the signs of the function or the number line. Let us see how. This is our number line included, including negative 1 and 1. And by looking to the sign of x squared, you can see it is positive. So it's supposed to be positive outside the region, outside these numbers. So it is going to be opposite in between. So you need to know the sign of your function between 1 and 3 by using the number line from here. From 1 till 3, sorry, from 1 till 3, you can see that it is positive. From 1 till 3, you can see that it is positive. So if the function from 1 to 3 is positive, so its integration is positive. Now I give you many ways and you can use more. Let's go now to another theorem, which is theorem number 9. If f of x and g of x are integral on an interval a and b, we said integral means the limit exists and we can calculate area. And if f of x is bigger than g of x, that means the region of the function f of x is bigger than the region of the function g of x for all x belongs to its domain from a to b. And because the region here is bigger than the region here, so the integration is bigger for f of x than g of x. Let us see that. Then the integration, which is the area of a and b of x d over x, will be bigger than and greater than the integration from a and b of g over x. That makes sense. Because if the region of f of x is bigger than the region of g over x, so the area of the first function will be bigger than the area than the second function. Examples, we can say that the integration from 1 to 4 of fx dlx is smaller than or equal to the integration from 1 to 4 of x cubed dlx. You can prove that by many ways. You can use also graphs. You can draw x squared and you know how to draw it. And you can draw x cubed and you know how to draw it. And discuss them or compare between them. You can see that the region of x squared between 1 and 4 is smaller than the region of x cubed between 1 and 4. That means their area should be, or the area of the first should be smaller than the area of the second. Now I'm going to give you other ways. One of them, you can choose a number between 1 and 4, then replace it instead of x in each. Then you can compare. For example, let me choose 2 and let me substitute it in the first, that will make it 2 squared, and replace it in the second, that will make it 2 cubed. And you know that 2 squared is 4 and 2 cubed is 8, and 4 always is smaller than or equal to 8. So that means that the first function is smaller than the second. That will make the area for the first is smaller than the second. Then let's have another way. We can let the first function, which is x squared minus x cubed, equals 2. Take x squared as a common factor and keep 1 minus x. That means you are using the difference between the two functions to study their signs, if they are positive or negative. So you can know that x squared is positive always for all real number. And you need to discuss the sign of the other function, which is 1 minus x. But you can use now that way to study each sign, which we call it building the function method. Building the function method. That means I'm going to start by the given x and start to build it and then study its sign. Let's do it by the first function, which is x is defined with me here from 1 to 4. This is my interval from 1 to 4. So x is between 1 and 4. Let's square each side because I want to build the first function. Square each side. That will make it 16 is bigger than or equal to x squared, bigger than or equals to 1. That means x squared is a positive value, and it is really positive because it is between two positive numbers. And without doing that all, you know that x squared is positive always for all real values. And again, I need now to study the sign of the other term, which is 1 minus x. You can build it again from 1 to 4 and go back to your function and see that your x is multiplied by negative 1. So let's multiply each side by negative. And multiply by negative will change the inequality from bigger to smaller. From bigger to smaller to make sense. That means you will get here negative x is bigger than or equals to negative 4 and is smaller than or equals to negative 1. And that makes sense because negative 4 is smaller than negative 1. Then you need to add 1 to each side to build your function. Watch it. Add 1 to both sides. You will get 1 minus x here bigger than or equals to negative 3, smaller than or equals to 0. Then you can discuss the signs for each. You know that x squared is positive and 1 minus x is negative because it is smaller than 0, is negative. So you are multiplying positive by negative amount. That will make the whole amount or the whole expression is smaller than or equal to 0, which is negative. So positive times negative will be negative. Now, after expanding this bracket, you will go back to your function, which is x squared minus x cubed, which is still negative. If you're going to move this negative x cubed to the other side, you will get exactly x squared is smaller than or equals to x cubed. Or you can integrate both sides like that. Then you can integrate from 1 to 4 for the left side, which is x squared minus x cubed dx. And if you integrate to 0, you will get 0 because the area of no region it's 0. Now, according to theorems, you can let this integration get in for the first and get in for the second. And that will be exactly like that. Integration from 1 to 4 for the first one, x squared dx, sorry, there is square here, minus integration from 1 to 4 for x cubed dlx, smaller than or equal to 0. That will allow this negative to be moved to the other side and to be like that. Integration from 1 to 4 for x squared dx will be smaller than or equals to integration from 1 to 4 for x cubed dx. And that will be the provement for our example. Watch it. Whatever you would like, use. You have many ways and you can have more. Finally, you need to prove that if the function the first function is bigger or smaller than the second, so the integration of the first function gonna be bigger or smaller to the second. And that makes sense. Let's go to the last theorem, which is theorem number 10. If we have k and l are two numbers and f of x is bounded between K and L. It's bounded between K and L. So that means it has limits from K and L for all x belongs to its domain from A and B. And the f is integral. We understand before how many times. What do I mean by integral? I'm going to repeat it. It means the limit of the summation of f of x multiplied by d of delta x exists and the area can be calculated on the interval from a and b, then the integration for the whole function from a to b f of x dlx will be bounded also. So the area will be bounded also between the first limit, k times b minus a, and the second limit, which is l times b minus a. And we can call this k b minus la is the lowest or the lower limit. And this we can call it the upper limit. Let's have some examples. Examples, find the upper and the lower limits for each of the following integrals. To do that, we are going to use theorem number 10 by building the function. A, integration from 1 to 3 of the function 2 over x plus 1 dx. Solution, by using building the function method. Always you have to use that way. It is the best and it is the easiest for this theorem. How to build it? As we said before, you are going to start by the interval of x, which is defined from 1 to 3. Be sure to write 1 smaller than a 3 and make sense when you are writing this statement. Now, you need to build the function. To build it, go back to your equation and see x is added to 1. Is added to 1. So you're going to add 1, then flip your function to make it down, then multiply each by 2, then integrate each side. So you have 4 steps to build this function. Let's do it step by step in front of you. X should be added by 1. So we're going to add each. This will be 4 and x plus 1 bigger than or equals to 2. I add 1 to each. And adding and subtracting do not change the inequality symbol. Only if you multiply or divide by negative. Then you need to flip each. That means if you're going to flip each, you will get 1 over 4 and 1 over x plus 1 and 1 over 2. Why you flip it? You can because you have x plus 1 down in the denominator, so you can't keep it up. You have to flip each. And you can see that when you flip it to make sense, 1 over 4 become smaller than or equals to 1 over 2. Always makes sense when you are making each step. Makes sense. If you're going to see that 1 over 4 smaller than 1 over 2, try to flip or change the inequality symbol from bigger to smaller. Just make sense to your statement. Let's go to the next step, which is we're going to multiply 2 to each. If you're going to multiply here 2, you will cancel 2 with 4 to get 1 over 2. If you're going to multiply 2, and also remember, you're going to multiply only that 2 to the numerator, not to the denominator. Be sure to remember that. And you're going to multiply it here also. And 2 divided by 2 will make it 1. And you will keep the symbol of the inequality as it is to make sense. Because half is always smaller than or equals to 1. Then you need to integrate each side and use theorem 2. What do I mean by that? That means when you're going to integrate a constant, theorem 2 said when you are integrating a constant, you're going to keep a constant outside and multiply it by b minus a. This is what will happen now. If you integrate a constant, you are going to keep it and multiply it by b minus a according to theorem 2. to integrate left and right sides. You will get exactly like that. Half is the constant, keep it, multiplied by your interval from b minus a, which is 3 minus L1, smaller than or equals to. The integration here is not constant, you should write it. Integration from 1 to 3 of the function 2 over x plus 1 dx, which is your your function, is smaller than or equals to. Again, you are dealing with theorem number 1 in that side, which is the right side. 1 stays as it is as a constant value multiplied by b minus a, which is a 3 minus L1. Now, after you calculate each side, you will get from here 3 minus 1 is 2 divided by 2 is 1. And this stays as it is because it is unknown, which has variables. Keep it. Divided is smaller than or equals to. Here also 3 minus 1 is 2 multiplied by 1 is 2. So you can see that your integration from 1 is 2 is bounded by the lower limit, which is 1, and the upper limit, which is 2. And this is what we are looking for from the beginning of the question. Upper limit is 2 and the lower limit is 1. This is our question. Find upper and lower limits. Let's have another example. Example number 2. It is talking about integration from negative 2 till 1 dx over x squared plus 1. Actually, we can write dx instead of 1 here. There is 1 here. Sometimes we can write it, sometimes no need. Let's prove it by the same way, by using the building the function method. Building the function method, because this is the suitable way or the method that we can use. By starting from our domain. Our domain is defined from negative 2 till 1. I think we're going to go back here and see what is going on with x. It is squared first, and then added by 1, and then we're going to flip it down, then we're going to integrate it. Let's do these 4 steps again. Then here we have a property. We didn't discuss it before, so I want you to take care about it and understand it first before we're going to continue. You're going to use this property to square both sides. If there is x between a negative number and a positive one, between a negative number and a positive one, and you want to square each, what will happen? You will get x squared here, and you know that x squared can't be negative. It's always positive. So that means it is going to be always bigger than or equal to 0, which is going to be also smaller than or equals to the biggest number squared, or the square of the biggest number. This can be written in that way. X squared in the middle, and you have to write instead of these two numbers 0, because it is always this function bigger than or equal to 0. Because x squared always, when you're going to remember its graph, it's always positive. And it is smaller than or equals to the biggest squared number. That means if you square the 1, you will get 1. If you're going to square negative 2 times negative 2, it is positive 4. So you're going to take the biggest, which is 4. If you want to understand this more, sketch it, graph it, and you can see that your x squared is between 0 and 4. Then you need to complete your building by adding 1 to each side. That means you will get here 1 smaller than or equal to x squared plus 1 smaller than or equals to 5. This is after adding 1 to each side. Now we need to flip, and make sense when you are flipping. Flip each side 1 over 1, 1 over x squared plus 1, and 1 over 5. And you can see that 1 is bigger than or greater than 1 over 5. Because of that, to make sense, we switch between the inequalities symbol. and we make this bigger and this bigger. Integrate each side now to finish your building. You will get, according to theorem number 1, you will get 1, which is the constant value, multiplied by b minus a. B minus a. And you know that you have here b is 1 and minus the minus will be positive 2. Bigger than or equals to the integration from negative 2 till 1 for the whole function because we completely build it here. Bigger than or equals to, again, use theorem number 2 to calculate this side. Keep the constant outside, multiply it by 1 plus 2. And we say that we're going to say b minus a. b minus a. Now you will get finally that result. A 3 is bigger than or equal to the integration of negative 2 till 1 of dx over x squared plus 1 bigger than or equals to 3 over 5. So this is the upper term and this is the lowest term. The upper limit is 3 and the lower limit is 3 over 5. This is our lesson for today. Thank you for listening, and I hope if you have any comments to write it for me to discuss it with you. And if you have any problem somewhere, please write your comments for me to explain it for you in another time. And next lesson, we will have some applications about these theorems and more examples and more exercise. So be ready for the next lesson. Thank you very much. Goodbye.